Have you ever wondered how scientists can make these huge, sweeping claims based on what seems like a tiny amount of data? Well, it's not magic, it's statistics. And today we're going to put on our detective hats and see exactly how statisticians use clues hidden inside data to uncover the truth.
So let's start with a really big question. Think about it. How can we possibly know if a new medicine actually works if we can't give it to every single person on the planet? It seems impossible, right? Well, this is the exact kind of mystery that statistical methods are built to solve.
This really gets at the core of what statistics is. See, probability is when you know the rules, like you have a fair coin, and you try to predict what's going to happen. But statistics? It's the complete reverse. It's like you find a random coin on the street, you flip it a bunch of times, and then you use that evidence to figure out if it's a fair coin to begin with. We're working backward from the clues to understand the bigger picture.
Okay, so every good detective story kicks off with gathering clues. And for us, our clues are our data. But before we can make any sense of those clues, we have to understand the entire scene of the crime, the whole context that we're investigating.
First up, we have this idea called the population. Now, in statistics, this doesn't just mean people. It's the entire group of things we want to understand. It could be every single light bulb a factory will ever make, or every voter in a country. You can think of it as the whole story.
But here's the big problem. The population is almost always way too big to study directly. Imagine a factory that makes batteries. If you wanted to find out their average lifespan, you couldn't possibly test every single battery, because then you'd have none left to sell. It's just not practical.
So, what do? We take a sample, and a sample is exactly what it sounds like. It's just a small, manageable piece that we pull out from the population to actually examine. These are our fingerprints, our DNA evidence, our witness statements. They are the clues we can actually get our hands on.
As you can see, the sample is just a tiny little piece of that much bigger population. And maybe the most important job for any statistical detective is to make sure that this small group of clues really represents the whole picture. Because if your sample is skewed or biased, all your clues are just going to point you in the wrong direction. All right, so we've got our clues from the sample. Now what? Well, the next step is to analyze that evidence to make a really smart, educated guess about the entire population. And this whole process is called estimation. Let's go back to our light bulb example. Let's say we test a sample of 30 bulbs, and we find that their average lifespan is 788 hours. That number, 788, that's what we call our point estimate. It's our single best guess for the average life of all the bulbs based on the evidence we have.
But, and this is a really important but, is the true average for all the light bulbs exactly 788 hours? Probably not. Almost certainly not, in fact, right? If we grabbed a different sample of 30 bulbs, we'd probably get a slightly different number. Our one sample is a really important clue, but it's not the whole truth.
A good detective doesn't just point to one suspect and say, "That's the guy." No, they identify a range of likely suspects, and that's exactly what statistics does with something called a confidence interval. Instead of one single number, it gives us a range of believable values where the real answer is probably hiding. It's our zone of likely suspects. Now, this formula might look a little intense, but the idea behind it is actually super simple. All it does is take our best guess, that 788 hours, and then it builds a little buffer around it. We call that buffer the margin of error. And the result is a range, say from 780 to 796 hours, where we can be pretty confident the true average for all the bulbs actually falls.
So that's how we estimate things. But what if we need to test a specific claim someone is making? Well, for that, statisticians have this really cool formal process that works almost exactly like a courtroom trial. We literally put the claim on the stand.
So in this statistical trial, you have two competing stories. First, there's the null hypothesis, which we write as H0, or H0. This is like the defendant. It's the status quo, the current belief. We assume it's innocent unless the evidence is just overwhelming. On the other side, you have the alternative hypothesis. This is the prosecutor's case. It's the new, exciting theory that we're trying to prove is true.
And just like a real trial, this process follows 5 clear steps. First, you state the charge. What are the null and alternative hypotheses? Then, you set the standard of proof, kind of like beyond a reasonable doubt. After you set the rules of the court, you present the evidence, the data from your sample. And finally, you reach a verdict. Is the evidence strong enough to convict the null hypothesis, or does it walk free?
But here's something that is absolutely critical to remember. Just like in a real courtroom, the verdict can be wrong. These statistical decisions are all based on probability, not on absolute 100% certainty. And that means there is always a risk of making a mistake.
So in any verdict, there are really 4 possibilities. 2 of them are good. Those are the correct decisions. We either correctly acquit an innocent null hypothesis, or we correctly convict a guilty one. But that leaves 2 other boxes, the 2 ways we can get it totally wrong. Let's look at those.
A type 1 error is what happens when we reject the null hypothesis even though it was actually true. In our courtroom analogy, this is a terrible outcome. It means we've convicted an innocent person. The evidence we had looked really strong, but we still came to the wrong conclusion.
And a type 2 error is the exact opposite mistake. This is when we fail to reject the null hypothesis, even though it's actually false. In court, this is like letting a guilty person walk free. They really did it, but our evidence just wasn't strong enough to prove it. So the next time you see a news article or a study that's making some big claim, I want you to think like a statistical detective. Remember that whatever conclusion they reached, it's based on clues from a small sample, not the whole population. So ask yourself, what claim was actually being put on trial here? Just how strong was the evidence? And what's the real story that these clues are telling us?